On October 16th, a flight controller at NASA's Jet Propulsion Laboratory sent a routine, almost boring command out toward Voyager 1, 15 billion miles away. Turn on one of the spacecraft's heaters. It was the kind of instruction the team had sent thousands of times before over nearly 5 decades of operating this particular spacecraft, never expecting it to be anything other than routine. Nobody in that control room had any reason to think this particular Wednesday would be any different from countless other ordinary operational days spent quietly managing the most distant human-made object in existence. 46 hours later, the response came back, and it was not what anyone was expecting. Voyager 1 had gone quiet, not fully silent, not yet, but its main communication channel had dropped to a fraction of its normal strength, and within days, it would disappear entirely, forcing NASA's engineers into one of the tensest recovery efforts in the mission's entire 47-year history, one that ended with an almost unbelievable twist. The most distant human-made object in existence phoning home using a radio transmitter it hadn't switched on since 1981. This is the true story of what actually happened when Voyager 1 sent NASA something nobody in that control room had planned for, and why the incident revealed something genuinely unsettling about just how little safety margin this legendary spacecraft actually has left. To understand why a simple heater command could spiral into a genuine crisis, you have to understand exactly how thin Voyager 1's operating margins have become after nearly 50 years in space. The spacecraft runs on 3 radioisotope thermoelectric generators, essentially containers of decaying plutonium that convert heat into electricity, and that electricity every single year as the radioactive material inside continues its slow, irreversible decay, a process no amount of clever engineering can pause, slow down, or reverse. To keep the mission alive for as long as possible, engineers have spent the past decade methodically shutting down one system after another, turning off instruments, heaters, and non-essential hardware in a carefully sequenced retreat, preserving just enough power to keep the spacecraft's most absolutely essential to keeping Voyager 1 alive and communicating had already been switched off years earlier, which meant there was very little room left to accommodate any kind of unexpected power draw, however small, a spacecraft operating so close to the edge of its own survival that even minor miscalculations now carry consequences they never would have carried decades earlier. That's exactly the situation the October 16th heater command walked into. On paper, turning on a single heater should have been well within Voyager 1's available power budget, an operation the flight team's own computer models predicted the spacecraft could handle without any trouble. But somewhere in the execution of that command, something drew more power than expected, and Voyager 1's automated fault protection system, a piece of software built specifically to protect the spacecraft from exactly this kind of dangerous power overdraw, kicked in entirely on its own, with no human involved in the decision at all. Fault protection systems like this exist on essentially every deep space mission for good reason. If a spacecraft draws more power than its supply can handle and nobody catches the problem in time, the entire mission can be lost in minutes, with no possibility of physically inspecting or repairing the hardware from 15 billion miles away, no repair crew that could ever be dispatched. No way to intervene manually if things go wrong faster than a signal could travel from Earth to fix it. So when Voyager 1's fault protection system detected a problem, it did exactly what it was designed to do. It started shutting down non-essential systems automatically to bring power consumption back under control without waiting for. This is precisely why fault protection systems are built to act autonomously in the first place. By the time a distress signal reaches Earth and a response gets sent back, a genuinely dangerous power crisis could have already destroyed the spacecraft twice over. Here's where the story took its first genuinely alarming turn. On October 18th, engineers at NASA's Deep Space Network, the global system of massive radio dishes responsible for communicating with every deep space mission the agency operates, couldn't find Voyager 1's signal where they expected it to be. After some searching, they eventually located a much weaker version of the spacecraft's usual X-band transmission, confirming that the fault protection system had lowered the rate at which the transmitter was sending data home, a power-saving measure that also shifted the exact signal characteristics the Deep Space Network needed to search for. The team began investigating immediately, trying to understand exactly what had triggered the response, and how serious the underlying issue actually was. Then, the following day, October 19th, the situation got considerably worse. Voyager 1's X-band transmission, the spacecraft's primary, most powerful communication channel, the one it had relied on for the entire mission, stopped entirely. Piecing together what had happened from the fragments of data they could still access, engineers concluded that the fault protection system had likely triggered 2 additional times. In the hours following that first, or anticipated, it shut off the primary X-band transmitter completely and switched Voyager 1 over to its secondary radio system, a lower power backup called the S-band transmitter. That detail is where this story becomes almost impossible to believe. The S-band transmitter had not been used, not even once since 1981, back when Voyager 1 was still relatively close to home, freshly finished with its flybys of Jupiter and Saturn, decades before it would ever cross into interstellar space. It had simply been sitting dormant inside the spacecraft for 43 consecutive years, an old backup system nobody expected to ever need again, quietly waiting in case exactly this kind of emergency ever forced its hand. The problem with the S-band transmitter wasn't whether it would still technically function after 4 decades of complete inactivity. It was whether anyone on Earth would even be able to hear it once it started transmitting. The S-band system uses considerably less power than the X-band transmitter Voyager 1 normally relies on, the spacecraft's dwindling electricity supply. But that lower power comes at a direct cost. A significantly fainter signal, one engineer's worried might simply be too weak to detect across the staggering distance now separating Voyager 1 from Earth. A gap that had grown enormously in the 43 years since anyone had last needed to listen for exactly this frequency. When the S-band transmitter had last been active in 1981, Voyager 1 was still comfortably inside the solar system. By October of 2024, it was sitting more than 15 billion miles away, deep in interstellar space, trying to whisper home across a distance the original transmitter had never once been tested against. For several tense days, NASA's engineers worked to locate the faint, decades-dormant signal somewhere in the noise picked up by the Deep Space Network's massive dish antennas, uncertain whether the attempt would even succeed. On October 22nd, they sent a cautious command specifically, designed to confirm whether S-band communication was actually possible, and on October 24th, NASA formally announced that contact with Voyager 1 had been re-established. The spacecraft was alive, stable, and once again able to receive commands and send back basic engineering data, all of it now flowing through a communication system that had spent 4 decades in complete silence, reactivated only because an ordinary heater command had spiraled into exactly the kind of emergency that system had been built, and then forgotten about, to handle. Even once contact was restored, the team faced an uncomfortable decision about what to do next. Simply commanding Voyager 1 to switch back to its normal X-band transmitter carried real risk, since nobody yet fully understood what had triggered the original fault protection cascade in the first place. And sending that command risked tripping the exact same sequence of automatic shutdowns all over again, potentially with a worse outcome the second time around. So rather than rushing to restore the stronger, more familiar communication channel, engineers made the deliberate choice to keep operating cautiously through the weaker S-band system for the time being, using it to command the spacecraft, confirm its antenna was still correctly pointed at Earth, and slowly gather the information needed to understand exactly what had gone wrong before attempting anything that might provoke a repeat performance. Here's the part of this story that genuinely deserves more attention than it got at the time, because it reveals something considerably more unsettling than a single close call safely resolved. Voyager's own flight team maintains detailed computer models specifically designed to predict how much power the spacecraft's various heaters and instruments should require under any given command, models built and refined over nearly 5 decades of operational experience with this exact hardware. Those models predicted that turning on a single heater should have been a routine, unremarkable operation, well within Voyager 1's available power budget. It wasn't. Something about the spacecraft's actual present-day condition, whether a subtle change in one of its aging systems, some gradual drift in its true power consumption that the models hadn't fully captured, or simply the accumulated wear of nearly 50 years spent operating continuously in one of the harshest environments any human built it, object has ever been placed into, caused reality to diverge meaningfully from what decades of careful modeling had predicted. That gap between prediction and reality is exactly the kind of thing that should genuinely concern anyone following this mission closely, because it suggests Voyager 1's true operating margins may be considerably thinner and considerably less predictable than even the team managing it fully realized going into that October morning. This incident didn't happen in isolation either. It landed less than a year after Voyager 1 had already survived an entirely separate, arguably even more serious crisis, when in November of 2023, a corrupted memory chip caused the spacecraft to transmit nothing but unreadable, garbled data back to Earth for 5 consecutive months, a problem engineers eventually traced to a single failed component and solved only through an extraordinarily delicate, months-long remote repair process conducted across a communication delay of nearly 2 full days per exchange. Bill Kurth, a research scientist at the University of Iowa who has served on the Voyager science team since 1974, described the team's reaction to finally reestablishing full communication after the earlier crisis as pure elation, calling the recovery effort nothing short of a miracle performed by the engineers at JPL. Less than a year later, that same team found itself scrambling through an entirely new crisis, this time triggered by nothing more dramatic than a single heater command, a stark reminder that Voyager 1's continued survival has increasingly become less a matter of routine operation and more a matter of engineers. Repeatedly, resourcefully improvising their way through problems nobody could have specifically planned for decades ago. That same year, the Voyager team also found itself reaching for other, equally improbable solutions to keep the spacecraft functioning, including reactivating a set of backup thrusters that had gone unused for years, specifically to help keep Voyager 1's antenna correctly pointed at Earth as its power margins continued tightening. Taken together, the picture that emerges from 2024 alone is one of a mission increasingly held together by a combination of extraordinary institutional memory, decades-old engineering documentation dug out of physical archives, and a genuine willingness to gamble on long dormant hardware simply because there is no other option left. All of it playing out across a communication delay approaching 2 full days for every single exchange on a spacecraft whose original designers never imagined it would still be operating anywhere close to this long, let alone from this far away. So what does an incident like this actually tell us, beyond the simple fact that Voyager 1 survived yet another close call? It tells us that even the most experienced team in the world, managing a spacecraft they have operated continuously for nearly 5 decades, can still be caught genuinely off guard by what this particular machine does next, because the mission has now stretched so far beyond anything its original engineers ever planned, for that even the most carefully maintained predictive models are starting to show real cracks. Every additional year Voyager 1 survives is a year spent operating meaningfully outside the boundaries of what anyone ever expected it to do, which means every routine command, even something as simple as switching on a single heater, now carries a small but genuine chance of triggering a response nobody saw coming. That's precisely what happened on October 16th, 2024. And it's very likely not the last time it will happen before this particular spacecraft, older than the internet itself, finally goes silent for good. If stories like this are what you come here for, hit subscribe, turn on notifications, and let me know in the comments whether you think NASA will ever risk switching Voyager 1 back to its stronger X-band transmitter, because after everything this spacecraft has already survived, betting against it has never once been the smart move.